All right, so our next speaker is Jimmy Ba. He's going to talk about using fast weights to attend to the recent past.
Right. Hi, everyone. So this is a joint work with Jeffrey Hinton, Vlad May, Joe Lebo, and Kathleen Ionescos. Right, so let's get started. Just good old stories about RNNs. In RNN, we have a set of weights that connect between the hidden layers. And if you think about those weights, like those ordinary slow varying weights as a memory storage device, then effectively they encode the long-term information about the entire data set. And in fact, they learn the knowledge about how to map from a particular input pattern to a desirable output. And they're slow varying because at the end of they only change at the end of the sequence through some gradient descent algorithms. Then we have the second set of variables in RNN, which is the hidden states and hidden vectors. And those things encode very recent histories about the input in the sequence. And they change at every time step. And they have two roles, actually. One is to learn integrating information from the past in the sequence. And second role they have is, in fact, learning a good representation for the final classification task, or whatever the final task you have. So the question is, what about the short-term temporary informations? Where do we store them in RNNs? Right. So you may imagine if we have you want to have RNN that are able to use the intermediate computations and reuse them in the later time steps, then one potential solution is to have those hidden states to carry over those computation and remember them in their vector states. So at later state, they can be retrieved. But this is vastly very inefficient and clumsy, right? Because now we're burdening those hidden vectors, the hidden states of the RNN, to have a third row, which is remembering all those intermediate computations. And so the solution here is to think about what happens in the real recurrent neural networks, like our human brain. And the synapse, human brain actually has very dynamic and very different time scale learning rules and dynamics. So if we apply this idea to the artificial neural networks, then we have those slow weights, which is the traditional weights that you learn from backprop. And then we have those fast weights that can change rapidly and only encode the information for a particular sequence. So the idea of using two weights on each connection of the neural networks has been explored previously. And so Hinton and Plaut in 1987 has investigated such idea to use them to deblur memories from the neural network learning. And Schmier-Huber in 1997 actually pointed out that you can, in fact, learn such system through backpropagation end-to-end. But surprisingly, there have been very little practical applications and investigations of those ideas. I guess in 1993, the MNIS is still considered a very large-scale data set. So let's start with the ordinary RNN and to see how we can incorporate this fast weights ideas. So in a traditional RNN, you have those bottom-up input, those X, that encoded through the bottom-up weights C, and have those recurrent weights W that consider the past informations. And the information from the past and the bottom-up are integrated through these additive interactions, passed through some nonlinearity F. And to use the fast weights here, one particular solution is instead of having two different weights on the same connection, we can introduce these intermediate steps in between the recurrent computation. So now we can forward the previous bottom-up influence and the recurrent inference to this new intermediate step. And we process the information, refine the previous hidden state from the slow weights through this new weight matrix called A. That's a variable that changes depending on the time step of the sequence. So conceptually, one way to think about this idea of fast weights is that we have slow weights that learns the desirable input and output mapping And we have those fast weights that kind of clean things up with this contextual overlay to store those important temporary information from the past history of this sequence that can be reused in the computation. And so why do we just stop at one particular intermediate step, right? After all, in deep learning, it's all about squeezing more layers in between our models. So then we can introduce this so-called inner loop. So we can have not just one particular fast weight iteration, but also multiple steps. The reason why we want to do this will be clear in the next slides. So we can think of different learning rules for the fast weights. Instead of using an iterative learning rule like backprop, an alternative is actually doing this one-shot learning from borrowing from the Hopfield network. So at the end of each inner loop iteration, the fast weights are being updated by an outer product of the most recent hidden states. And that's being added to the previous fast weights. So effectively, you can think of this model as embedding a Hopfield network inside an RNN. So then thinking back to all those intermediate steps between the recurrent time step, those inner loops, effectively what they're doing is to retrieve the information that's being stored in the Hopfield net. And the entire system can be trained with backprop. And we apply this model to various tasks and start with the very simple toy problems. Right? So an RNN reads over a particular string that composed of characters and number pairs. And so each character is like a key in this case. And after the RNN has read over the entire string, we can ask the model to retrieve a particular key value in this case. So what's the number after C? And then the model figure out it has seen the C in the beginning of the sequence and output 9. And we can generate a whole bunch of such sequence. And the query key is uniformly sampled from the entire sequence. So the goal to solve this, so the one solution to solve this problem is to effectively memorize all the possible key and value pairs that's being encountered in this entire sequence. Then we want to compare with the various models in this very toy example. The fast weights outperform and the normal RNN. So the fast weights are able to solve this problem with significantly less recurrent units than like RNN and even compared to LSTM and still perform those models. So in fact, it's not very surprising to see this result because we designed those fast weights to have this auto-associative learning rule, and its goal is to remember the recent histories in the sequence. So what's more interesting is to look at this recursive vision task. And we can have, so the goal here is to, given an image of 48 by 48 image, we want to classify the facial expression into 6 different categories. And one can imagine that you can design and write a computer program to do this, which is the following program. And effectively what this program does is it takes the input image, the face, and it looks for all the facial features within that image. And also for every facial feature, it integrates and aggregates those facial expressions in the end to return that as a prediction. But this program also recursively applied the very same algorithm to the sub-facial expressions within those each sub-features. So this is a very recursive program. And let's look at how we can design RNN to solve or even to mimic the behavior of such program. So we can start by looking at the sub features of this face. And so here we're considering the problem where the control signal for RNN is actually given. So we know where to look for those subparts of the object within an image. So the goal is to test whether our model have a significant memory capacity to actually solve this recursive task. So in RNN, when given finding those facial features, the information is being integrated through the slow weights W here. And if we want to recursively examine the subfacial parts, which would be like the eyebrows of the eye instead of just the eye and the mouth, then so while we're examining the eyebrows and the nose, we can use the same slow weights to perform such computation. But the problem here is that now where do we store all those informations? So in the traditional ConvNet, all those informations of the intermediate computation is being carried out in your feature map at different locations simultaneously, and you will remember all those things all the time. But if we perform this task sequentially, we want to have some kind of stack-like mechanism. And in fact, we can apply our fastweight to mimic the stack behavior here. So you can modify the traditional RNN here by introducing this clear-out connection, which effectively wipe out the entire hidden state here at the beginning when you decided to go into a subroutine of the program. And so because we are updating our fastweights at every time step, so the intermediate computation here is actually being stored already in the fastweight. And we can perform some recognitions of the eyebrows and things before we go back to look at the eyes. And when we want to really pop the intermediate computation back, we can execute the fastweights and perform the retrieval inner loop to get information. So now we compare this model with the rest of the other RNN architectures, and also the ConvNet, which carries out all those intermediate computation at any given time. So the fastweights actually perform much better than the rest of the sequential model, but not as good as the ConvNet, but the performance is really close. Then we also apply this fastweights idea to learn a recurrent reinforcement learning agent. So in this game, the goal is to catch the falling pixel by controlling the paddle left and right. So you have two actions. And we can actually make this task a lot harder by only showing the first couple of frames when the ball is falling, and then the screen just go completely blank. It's like playing those very hardcore Tetris game where you only get to show the block's location the very first couple seconds, and you have to remember where it is and place your block accordingly. So in this case, you have to control the paddle to catch the ball at the right location by remembering the last frame you saw. So again, the fastweights model, which is the green line here, learns this task much faster than the LSTM models and the regular RNN. So we can revisit the fastweight update learning rule here, which is a rank 1. And if we expand the update rule all the way to the beginning of the sequence, what we notice is that the fastweights is literally just a summation of a bunch of rank 1 order products of the intermediate hidden activations. So we can gain two insights here. The first insight is that instead of storing this entire fastweight explicitly, which is n by n matrix, we can just store those intermediate hidden states. So it's very beneficial if the number of hidden units we have is greater than the length of the sequence. And if we examine this equation further in this, which is the equation describing the inner loop of the fastweight computation, we notice that the model effectively is doing a kind of attention mechanism that using scalar vector product. So what that means is that our fastweights model is actually providing a biological plausible interpretation and implementation of those recently very popular neural Turing machine and memory networks, and how those things can be actually implemented in the brain, because in the fastweights, we don't have to explicitly storing all those intermediate hidden vectors. Those can all be combined into the fastweights matrix, which is part of the internal storage device. So in conclusion, we present this fastweights model, which is a very powerful internal storage mechanism. And so the way it works is that the fast associative memory in the associative step, which is the inner loop, deliberately attracts the current hidden states to the previous similar hidden states through the Hopfield retrieval rules. And we found that when applying the layer norm, we can make this scalar product attention mechanism a lot more stable. By introducing those hidden storage, the internal storage device, now we feed those hidden states up to actually perform the working memory computation and learns a really good representation for the final classification task. So we believe that there's definitely many different ways to expand the memory capacity of the RNN, including neural Turing machines and memory networks. And also here we present the fast weights. And we're only at the beginning to explore the full potential of those memory components to RNN. So, yeah, thanks.
Questions? Yes.
I'm wondering if your construction might benefit from using models of associative memory with larger capacity.
Yes. So at first we thought, so this auto-associative rule from the Hopfield net is kind of clumsy. It's not that memory efficient because in fact you can only store the log n number of copies of the patterns. But when we compare with the associative LSTM in the first associative, so where the associative LSTM deliberately and explicitly construct this associative retrieval and memories, and we in fact outperform the model. So the reason why is because I think the Hopfield net here, or the auto product heaping-like learning rule, is trained through backprop. So they actually learns to utilize the capacity of the fast weights much more efficient than the traditional Hopfield net.
But I guess I'm asking if you can modify the update rule in your formula.
Yes, definitely.
In such a way so that the capacity of memory is larger.
Yes, certainly. So it's definitely an ongoing project. That's you can try something like an OAS rule and even error correction prediction rules. So you don't, instead of doing the one-shot update rule, you can have a prediction model that predict the storage pattern as well. So in this paper, we're just trying to present the most simplest model that shows a proof of concept.
In the back.
Hi, Jürgen Schmidhuber of the Swiss AI Lab ITSIA. Thank you for this very interesting presentation. I think there is a difference between your system and the other one that you mentioned, the ICANN 1993 system, which was very similar in terms of update rule for the fast weights and everything. However, it did not have this decay rate. And in your experiments, can you say how important was this decay rate to make it work? Or did it also work without any decay rates, just where the network itself had to learn to control all the fast weights without any prior decay built in?
Yes, that's a very good question. Because the nonlinear activation we use for Dr. RNNs is actually ReLU, so it does not have this behavior of the sigmoid where you have this upper limit of how excited those neurons can be. So in this case, the decay is actually very important to prevent the whole system to go unstable during the learning. And the decay parameter we use usually is around like 0.5 or like 0.3. So in fact, it remembers the past like 4 or 5 or 6 steps.
Well, thank you.
Yep.
Right here.
You mentioned at the beginning of your talk these two roles that the hidden units play, which was creating a good representation for the task and also integrating things into memory.
Right.
I'm just wondering if you can, like, I don't know, maybe convince me that you need to integrate things into memory, or that this isn't the same thing as just constructing a good representation for the task, or how would you distinguish those?
So you may imagine, like, for example, in the facial classification task, where a representation for those sub-objects may not be very important or informative for the final classification of the entire face. So knowing the eyebrows and shapes could be like totally useless representation. And because in the fast ways, you can just remember all those intermediate steps and retrieve the things that's only important for your final classifications. So the model effectively just ignore those uses. So you can actually, so those hidden representation frees up to do those things. Yeah. So the hidden states, you can imagine that after integrating all the information for the entire face, may not even include the final detail information about the mouth, because that's not very important to for the facial expression classification.
Okay, thanks.
While the other speaker sets up, I'm curious, have you tried actually deeper networks? Have you seen any sort of improvement by having several recurrent neural net layers deep using these fast weights?
Right, so in my experiment, no, I have not tried more than one single layer RNN. But I would imagine you may want to have some kind of like a multi-layer RNN that even have different scales at different levels. So meaning it has different dynamic scales where it's very much like clockwork RNN. So then you don't waste all those storage capacity at every time step at your higher levels.
All right, let's thank Jimmy.